Our next presenters are with ARM. We have Dong Wei, along with Matteo Carlini, and they're going to be talking about UEFI updates and open source firmware evolutions on ARM. Thank you.
I'm going to steal a couple minutes to update you on some of the specification efforts that we have done in ARM related to UEFI. And then Matteo is going to talk about the open source firmware evolutions on ARM. Basically, for the agenda, we have the UEFI related SBBR and EBBR updates. This is the part that I would cover. And then Matteo is going to talk about open source firmware evolutions on ARM, trusted firmware updates, secure software isolation recap, and firmware challenges for edge devices. So in ARM, for the ARM ecosystem, we have created a couple of specifications related to UEFI on the firmware side. The first one is the server-based boot requirements, which basically is defining the requirements of the interfaces necessary between the system and the operating system. And this is leveraging leveraging from the industry standards, UEFI ACPI and SM BIOS from the MTF forum. And we also take into account the TCG firmware specs and the PCI firmware spec as well. And ARM just joined the TCG again this week. And we also try to make a connection with these industry standards with some of the ARM specifications to fill in the gaps. So we define the PSCI, SMC, ARM fixed firmware hardware definitions, and the ARM management mode definitions as well. So for this specification, it's actually publicly available with the link on this page. We have an ARM-based specification license, and the contribution to this specification is done through this ARM Server Advisory Committee that we form with over 40 different vendors in the industry, anywhere from the silicon providers, BIOS vendors, operating system vendors, cloud vendors, and such, OEMs, ODMs. And we released the version 1.1 mid of last year. And we also released or launched the Server Ready program last October. And right now we're working on the content for the next revision. So that is mostly for the server space. And I think it probably also covers areas like the edge devices that are closer to the cloud. And maybe the client space could use some of this as well. So we're kind of looking into these different segments. But on the other hand, from the embedded space, and probably the edge devices that are closer to the edge, if you will, closer to the devices, we also define this specification called embedded base boot requirements. So this specification is for the A-class ARM processors for the embedded space, and it's intended for the embedded devices and the things edge devices. What I mean is the devices that are closer to the actual Internet of Things. And we developed this specification in the open, so you can find the specification in the GitHub, actually. The license is the Creative Commons Attribution Share Alike 4.0. and then we work with the industry because the embedded space spans quite a bit. A lot of people are interested in this space. And in that space also the U-boot has a device tree by both of those are very predominant. So EBBR is trying to establish a common interface with UEFI. So U-boot implementation or EDK2 implementation can present this UEFI interface to the operating systems for these devices. So that way we can abstract the interfaces so that the device development and the operating system development can be independent. Right now, with the traditional U-boot implementations, the OS and firmware implementations are very much tied together. But for EBBR, we do not require ACPI, but if people want to use ACPI, that's fine as well. So the contribution, like I said, is completely open. Anyone can contribute to EBBR, and it's a kind of an open source spec development. And we have, I think at this stage, a monthly conference call. It used to be weekly. And we just launched version 1.0 on the last day of March. And after version 1.0, we are going to look into the secure boot and capsule services for firmware updates. Because for 1.0, we just want to kind of make sure the UEFI interfaces are suitable for the embedded devices like that. And we also leverage, like I said, the PSCI, SMC, and also the trusted firmware A, which Matteo is going to talk about more. So we're going to continue to work in that space, and also we work with Lenaro on this. There are 96 boards are using this specification in the embedded space now as well. So it's an interesting aspect of how we marry UEFI to the embedded space. And with that, I will hand over to Matteo to talk about the open source firmware.
Thanks, Dong. Hello, everyone. Right, so I'm Matteo Carlini. I'm Director of Software Technology Management at ARM. And today I'm going to tell you what we are doing in the open source firmware space from ARM, both from a trusted firmware perspective and what we are doing also on UEFI projects like EDK2 and U-boot. So first of all, a news on ARM trusted firmware. So we presented in the past ARM trusted firmware at this venue during Plugfest events as an ARM open source project. Well, now it doesn't exist anymore as an ARM open source project because it's becoming, and it became, a collaborative open governance project. So it's a project open to everyone. Everyone can join. It got kicked off in October last year, and we now have 8 founding members. ARM is just one of the founding members. So the project provides the reference implementation of the secure word firmware for all the ARM-based devices. So Armv7, V8, and both for the A and the M class microcontrollers. It provides a reference implementation as well for the ARM platform security architecture. That's the security framework that ARM is driving for securing ARM-based devices. So it's there, it's alive, the charter is available online, all the informations are there. Get in touch if you want to know more. Now, in the past, I presented in this forum what we were doing in order to provide some sort of isolation in the ARM trust zone environment. So if you want to run services beyond the trust zone controller on ARM, how you can make sure to isolate these services, or how you can make sure to restriction to restrict what these services can access on the system from the secure world perspective, because you don't want your secure applications to have a view of the entire system and maybe compromise your entire system. So these are a set of requirements that are coming from a wide different set of market segments. So we are receiving these requirements from the IoT space, the embedded space, up to the cloud. So everyone that wants to leverage the trust zone-based security wants to have some sort of isolation and privilege restriction in the secure world. And these concepts must work on the existing ARM architecture, so 8.0, 8.1, 8.2 cores. And if we do it right, if we provide the software architecture right, then we also allow a seamless migration to the future architectures, so ARM 8.4 that provides a hardware-assisted isolation. We will see that in a minute. So that's a recap of the reasoning that is behind what I'm going to present. So a strong need for isolation, a strong need for privilege restriction in the secure world. So that's the picture that I presented last year here at the same venue. And that's the current situation upstream. So if you go to the upstream project, Trusted Firmware or UEFI EDK2, there are upstream packages and examples in the platform ports to achieve this scenario. So basically, you can run a UEFI service as standalone service in the secure world beyond the trust zone controller into what we call secure partition. That's basically an isolated execution environment that have a limited access to the system resources. And the whole concept in the secure world is managed by the underlying trusted firmware and specifically by a component that is called Secure Partition Manager. Right, so that's the situation up to today. It's based on the existing management mode spec, as Dong was saying, but it has few limitations. It only allows one partition to run, so one UEFI service at a time, and it's based on a run-to-completion model. So the normal world, once it kicks off the execution in the secure world, cannot reclaim the CPU cycles back. And that's a huge limitation that it's there at the moment. So we are already working, and we are working for a while now, on the evolution that will allow basically this picture. So the management mode specification is translating into something more complex that we are calling secure partition client interface. It provides a set of APIs for the normal world operating systems and the normal world hypervisor or UEFI environments to call multiple services in the secure world that can run concurrently, and they don't have to be on a run-to-completion model. So the specification allows for the normal world to reclaim cycles back. So not to have their cycles completely stolen by the secure world execution. Which are the use cases that we are trying to cover? A bunch of them are listed there. The typical one that we are hearing from partners, so on my system, I've got a secure storage in which I store my UEFI variables, and I want to read them from the secure world. So I execute a UEFI standalone for accessing the storage medium through the secure world. That's one. Firmware update is another one, very similar, accessing storage medium for storing your capsule or your binary blobs for updating the firmware. You can even implement a firmware TPM in one of these partitions, or you can implement errata handling or RAS error handling. And you can even implement communication to BMC into one of these secure partitions in the secure world. So you can really mix and match a lot of different services. The little gray box here is trying to show that the evolution of the ARM architecture, at some point, once we will have 8.4 based devices in the market, will allow secure virtualization. But it's grayed out because all this software framework, as I said, must work on the existing systems. So this must absolutely work on the existing ARM Neoverse cores for the infrastructure, on the ARM Cortex cores for the mobile, on everything. So this is currently in a cooking phase. There are traces of these scenarios as an evolution on the upstream projects, and the spec is currently in an alpha stage, and we are welcoming all the feedbacks from partners because we want to make it right, as we said, achieving all our partners' needs and different requirements. So is that it? That's what we covered. We are ready for the next challenge. Nothing more to cover? Not exactly. So in the past year, so I came here last year and I presented basically the same thing. What happened in the meanwhile is that we started to receive a lot of different requirements coming from the edge. So as Don was saying, our partners are starting to build devices, ARM-based devices for edge computing that look like this. So are basically computation entities that are much more similar to the cloud space than they were to the embedded traditional vertical segment. So they are kind of little ARM servers moved to the edge space, and they have a lot of different requirements and the different challenges for the open source firmware. And that's what I will try to describe in the next bunch of slides. So the edge has specific requirements for running standalone MM services in the secure world, because the edge wants to mix and match not only UEFI standalone MM services, but curiously, they also want to run trusted OSs in the secure world in parallel. Secondly, and I'll keep this second bullet point for the last couple of slides, these devices are traditionally U-boot device tree based, as Dong also mentioned. So we have a challenge. How can we expose UEFI services and ACPI to these devices? And the third one, as we are allowing partners to put different software that execute in the secure world, this software may come and will come from different owners, from different providers. So a BIOS vendor, a silicon provider, an ODM, and all of them will be signed differently. So we need some sort of new framework for authenticating these services, extending what we have right now, because I'm going to explain that right now we can only allow, let's say, one single chain of trust as an authentication method. So let's go one by one and see how we are trying to solve these challenges for the edge. So the first one is an evolution of the previous picture, in which, as I said, on the edge space, we are seeing partners that want to run trusted operating systems together with UEFI services in the secure world. So the secure partition client interface must take into account also these sort of requirements. So we are extending the specification to make sure that a normal world hypervisor or kernel can also invoke a service that runs as a trusted application on top of a trusted operating system. So it's no more only a UEFI standalone service that runs independently, but it's precisely a trusted application that is handled by a trusted operating system. And it may be whatever operating system, commercial one, open source one, as an ARM, we don't care. Obviously, the specification, the SPCI, is standardizing the communication between the normal world and the secure world. So there will be a standard set of APIs, and we will provide the needed changes into the open source Tiano Core EDK2 space for moving from the management mode specification to the SPCI specification. So you could leverage those changes into EDK2 to execute and to call multiple services into the secure world. And obviously, there will be changes in the underlying manager, into the underlying secure partition manager, that at this stage really becomes kind of a router. So it has to know where the request needs to land. So if the request needs to land into a UEFI standalone partition or into a trusted OS. And as I said, if we do it right, the transition between the previous model on the existing ARM cores and ARM architecture to the new one in which we introduce secure virtualization, the transition will be easy because the interfaces will be exactly the same. So ARM will provide a reference implementation, again, as part of trustedfirmware.org, the new community project. We are going to provide a reference implementation for the secure virtualization piece of software that we run at EL2. And mixing this virtualization extension with the new SMMU from ARM and the new interrupt controller from ARM, so all the pieces of the ARM architecture, then you will achieve full, complete, hardware-enforced isolation in the secure world. So I forgot to draw, but there should be some more dotted lines in, between every single partition that really gives the idea of an hardware-assisted isolation that is not possible only with a software model. So from a software perspective, we pretend these partitions to be isolated, but obviously this relies on the code running into the partition to play nicely with the other partitions. But there is no hardware enforcement here. The hardware enforcement will only come with this picture. So that's one evolution. The next one, so before going to the UEFI ACPI device tree topic that's kind of controversial, let's look at the multiple firmware sign-in domains. So here is the situation that we are basically allowing now with multiple partitions. So we have different pieces of software running in the secure world that may come from various different owners. As we said, ODMs, OEMs, BIOS vendors, or the silicon provider itself. And each of them will be signed differently, and each of them must be authenticated using the proper public key and the proper root of trust key, whatever is needed in the platform to authenticate this piece of software. And the last point, so we want this authentication mechanism to be independent one another. So we don't want to force or to ask the platform owner to re-sign everything with a platform key outside just because the ODM wants to update their pieces of software in the secure world. So the ODM should be able to deploy that independently from the platform owner as long as it provides the proper key and the proper signature that matches against that key. So where is the challenge? The challenge is, at the moment, with the upstream reference code, this is not possible. This is not possible because there is a single chain of trust that authenticates just one step at a time and one piece of software at a time in a cascading way. It all origins from the root of trust public key, so the green box at the bottom, and there is no way for extending this mechanism at the moment in an easy fashion to take care of multiple sign-in domains. So we are still investigating which is the best way to do that. So which is the best way to allow different owners to authenticate independently their pieces of software. So we are looking at something like this. I appreciate it's a bit confused. But basically, there will be a concept of multiple root of trust keys, if you want to call them that way. So there will be likely still a platform key that will be the master key for the platform, but there will also be some sort of UEFI normal world root of trust or public key that will be used throughout the different bootloader stages on ARM to authenticate different pieces of software in the secure world that belongs to different owners. And the important point is that we don't want to limit our partners to a restricted number of partitions, keys, or authentication steps. So we want some sort of flexibility. We want to provide our partners the flexibility to install whatever number of secure partitions they want in the secure world. So whatever number of public keys they want, they should be able to just deploy them and use them. We want to provide a framework that is based on open source software, just not to create too much fragmentation in this space from an authentication perspective. Last point. So up to now, we are pretending that these edge devices are typical standard server-based devices that have a clear separation between the runtime firmware, a hypervisor or a UEFI firmware that belongs to a BIOS vendor, and the traditional high-level operating system that is well described by its ACPI tables and all perfect, all fine. But unfortunately, this is not the reality. The reality, especially on the legacy base of edge devices, looks like this, more or less. So the silicon provider traditionally owns the trusted firmware layer, and it also traditionally owns the U-boot bootloader that describes the system using device tree. And then on top, there is no concept of high-level operating system, but there is an embedded, possibly Yocto-based custom kernel that again comes with a device tree description, is deployed possibly all together in a single BSP, hate this word, and it's deployed all together, and it's a traditional embedded vertical device. So newer systems may look like a bit more like the left picture, but all the legacy systems definitely look like the right one. And the problem that we have, the problem that our partners are raising to us is, oh well, but you know what? We want to mix and match. Because what we want to do, we want to do something like this. So we want to run a high-level operating system, a commercial Linux distribution, or a commercial operating system on top of these devices. Or we want to run a commercial hypervisor on top of these devices. And we don't want to change U-boot. It's legacy, it's deployed in field. There are millions of edge gateways that are U-boot based plus device tree. How can we make it possible? So we are still experimenting. There is no solution, no easy way out. Feedbacks are welcome and discussions are welcome. What we are trying to look at is something like this. So Dong was mentioning the U-boot extensions that will implement the eBBR spec. So there is a huge work going on in the U-boot project to describe all the boot services, the UEFI boot services, and there are discussions on how, if and how to implement runtime services. And this will basically expose some of the UEFI services onwards up to the operating system. And that's one point. The other point is how can we describe the system into ACPI based on device tree? So what we are experimenting at the moment is using the dynamic table framework that is now upstream into Tiano Core EDK2. It's a framework that we developed, and we have the maintainer here in the room, so if you have any questions, just get in touch. It's a framework for generating ACPI and SMBIOS tables on the fly at boot time, starting from an XML platform description that basically describes the hardware, describes all the CPU properties, all the system properties. We are trying to use this framework out of the traditional EDK2 space to generate ACPI tables using a device tree source file as an input. It's kind of a monster, I know, but as long as it pays the bill, it may work. Now, again, experimenting phase, if you have feedbacks, if you want to contribute, if you are interested in seeing how we can translate device tree into the ACPI, or which tables can we generate, because not all of them can be generated easily. Device tree allows for a lot of different system descriptions that are not easily described into ACPI. And the model of extending device tree and ACPI are totally different. So there are challenges, but that's what we are looking at the moment from an ARM edge point of view. That's it from my side. So if you have any questions, you have 10 seconds before Ryu starts to cry. If no question, I'll be happily come back to my desk. Oh, one question.
No, I just had a question about your secure world picture. When you had multiple entities that could sign things, is there the concept of only certain keys can authenticate certain kind of things, or is that part of the architecture as well?
So the concept is precisely that certain keys can only be used to authenticate certain pieces of software.
Yeah.
So the UEFI firmware will have its own key. Other pieces of secure world software will have their own keys, and so on. It will probably not be described by or mandated by the architecture. It will mostly be an implementation specific choice. What we want to do is provide a framework. If there is something to be specified from an ARM specification point of view, we will be happily update the specifications. But then it will be mostly reference implementation. So the thing is, there are existing ARM specifications that describe the left picture. Some partners are using this specification verbatim, and great. But if we are moving towards the right picture, that specification is not enough. So either we update the specification, or we throw it out and we provide a reference implementation. Obviously, if you want to standardize, at least having an updated spec will help. All right, thank you.